All right, this is 10.2 machines. Today we're going to talk about the mechanical advantage of machine and the efficiency of machines. So there are 6 different types of simple machines. You should probably write these 6 down just so you have them. All machines are made up of these 6 different types of simple machines. You put them together to create more complicated machines like a bicycle or all sorts of crazy things. And a machine is anything that changes the amount or the direction of work. So the first one here we have levers, seesaws, levers, or like a tire iron that you would take the tire off your car. That is a lever. We have pulleys. We have ramps, which are like our inclined planes that we dealt with forces. Wheel and axle, like a bicycle wheel. We have wedges. That's like an axe. Which I thought was really interesting when I was looking at wedges. I never realized that a knife is a wedge. So like imagine cutting up your vegetables. You're just like slicing it, but it's just a wedge. It's a really sharp wedge that it just allows you to apply the force to separate the food from itself.
Wouldn't it be a lever too?
If you're chopping like straight down, like it's on the tip and you're chopping straight down, then yes. But if you're just slicing straight down like this, then the axe is a wedge. But yes, it could be a lever. And then a screw, which there's some debate about the screw, whether it's a simple machine or a compound machine made up of I think it's a wedge and a wheel and axle. It's either a wedge and wheel and axle or a ramp and wheel and axle, but I'm pretty sure it's a wedge because it's like going down into something, wedging itself in there. But we call it a simple machine. Your book, I think, calls it a simple machine. Okay, so we got these. I don't see any red cups out, so we're going to go with moving on. The first type of mechanical advantage we're going to talk about is the actual mechanical advantage. And that is a property that we assign to these machines to kind of figure out how much it's helping us. And it's a ratio amount of the amount of forces. So how much force comes out versus how much force you're putting into the machine. For the most part, we want the force out to be larger. For the most part. So for instance, think of your tire iron, right? If you tried to stick your hand on the nut, bolt, whatever it is that holds that thing on there, it's going to take a lot of force. Like you're really going to have to pry it. And that's not going to work out well for you because it's really tight on there. But if we take a tire iron on it, which is a lever, and we apply the force as far away from the center as we possibly can, we don't have to push very hard. We still have to push hard, but not as hard as if we were trying to unscrew it with your hand. So it adds distance. You have to move more distance, but you have to apply a lot less force in order to do the same job. So the out force is the what do you want to do without the tool? Like what's the job? What's the goal? And the goal is to get the nut off the tire. And the in force, right here, the in force, is going to be using the tool. How much force do you need to apply to the tool to get that thing to come out, to do the job? So how much force are you putting into the tool? Your book uses the resistance force and the effort force, which I find a lot more difficult to conceptualize. So the resistance force, I just call force out. That's, what you want, what's being done. What do you want to be done? And the in force, the effort force, that's how much force you're putting into it. So the in and the effort, not too bad, but the resistance force is a little weird. It's a little hard to conceptualize. So we have the actual mechanical advantage is equal to the force out over the force in. And in your book, they call this FR over FE. Now, most of the time, not all the time, But most of the time, we want to increase force. So the force out, we want to be bigger. We want to make our job a little easier. Not all the time. My example at the end of this, we actually are decreasing the out force because we're on a bicycle. So we want to go a further distance. We don't really care how much force we put in. We want to go a further distance. So in that particular example, this one is not bigger. But for most of your examples, that one will be bigger. And this one will be smaller. For most of them. And that makes the AMA bigger than 1. So if you are looking for force to be increased, you're trying to make your job easier, this is true. But if you want to increase distance instead, the reverse of all of this. So that would be smaller, this would be bigger, and this is going to be less than 1. But that's an increase in distance, which doesn't happen very often, but like with the bicycle, which is my example, it does. But most of your problems in the book will be more like this. Remember, the notes are on Edline. Look at them on Edline. You don't get everything. And grab some cups if you think I'm going too fast. Good. Okay. So now let's talk about the other mechanical advantage. This is the ideal mechanical advantage, or the IMA. Now, I'm pretty sure your book calls the AMA just MA, and then it calls it the IMA. But I call it the AMA and the IMA. It's easier for me to remember which one's which. The ideal mechanical advantage is a ratio of distances. So, ideal mechanical advantage is going to be the distance in over the distance out, which is dE over dr. Notice that in AMA, out is on top, and IMA, in is on top. Again, for most of the problems, if you want a bigger force, you're going to end up with a smaller distance. And that's, if the goal is to lift something heavy and to make it not quite so hard for you to lift, or something like that, where you want an increased force. All of this holds true. The IMA will also be bigger than 1. But if you want a bigger distance out, like in the bicycle, again, switch all these things around. Smaller on top, bigger on bottom, it's less than 1. But for the most part, this is true. So what's the difference between actual and ideal mechanical advantage, other than the fact that it's based on force and distance? It's in the name. Actual mechanical advantage is how much the machine is actually making your job easier or harder. If it's more than 1, it's making it easier. If it's less than 1, it's making it harder. Force-wise. The ideal mechanical advantage, again, it says ideal. It's what the machine should be doing. So according to its distances, it's saying this is how much it should actually be helping you or hurting you. So the reason the actual mechanical advantage does not match the ideal mechanical advantage, and which is always, in real life, we don't have a 100% efficient machine, is because there's always some sort of energy that's lost in the process. And by lost, I don't mean destroyed. I mean transferred out of the system. So that is why it takes a little bit more force to make this machine go. Or, if it was ideal, it would take more. It would take less force, right? But it takes more force because we have to make up for that friction or that sound. Or anytime you have a sound, that's energy. Or anytime you have like a light, that's energy. It's like combustion engines are not very efficient because they give off so much heat and there's so much noise and so much light. Some of them get really hot and they start to glow a little bit. Okay, so how do I decide what's the force in, what's the force out? I mean, I already kind of told you that the force out is going to be what the tool is. So let's look at a couple of different ones. Here's a lever. Now the goal is to pop the top off the bottom. So the out force is going to be, how much force does this need in order to come off? So this would be F out. And I need to lift it that much because I want it off. So the out stuff is going to be what's happening to the bottle cap. This is how much force I'm applying to the bottle cap, and this is the distance that it's going to move. And the in stuff is how much force you're actually applying onto the tool. So there's a little small force on the tool, but look how much we have to move it. So this would be the D out and the D in. So it's a trade-off. Less force, but I have to move it further. Think of the tire iron. If you move it with your hand, a large force, but it's very small. You don't have to move very much. Whereas with the tire iron, you don't have to apply as much force, but you have to move it in that big, long circle to get it off. Here's pulley. Pulley systems are kind of weird. For the most part, the mechanical advantage of a pulley is going to be the number of pulleys. For the most part. For this one, if it's a mechanical advantage of one, it's not actually making your job any easier or harder. But a machine is not only changing the amount of work, it is changing the direction as well. So the pulley, even though it only has a mechanical advantage of one, is changing direction. Because for us, it's a lot easier to pull down than it is to lift something up, because we can use our weight more effectively. This one would have a mechanical advantage of 2 for the most part. In your book, I'm pretty sure that it just gives you distances and forces, so you can just calculate mechanical advantage this way. It won't be a whole number. But if you have any problems with that, it's usually the number of pulleys. Here's a bicycle, which we're going to talk about in our example. You can see that it's actually a compound machine because we have the gear here, the wheel and axle, hooked to a chain that is hooked to another gear and wheel. So we have a couple here. Now in this one, the forces look to be the same, but again it's changing direction. We want it to spin that way when we push on the pedal, and that's what's moving it around. So it may not be changing our force, but it is indeed changing our direction. Depending on what gear we're in, that'll change the force too. Inclined planes. These ones I think are honestly the easiest, but when you're looking at it, you're like, what's the out stuff? The out stuff is kind of hard. So we'll look at those real quick. Here's your inclined plane. What's the goal? We have this box. What's the goal? The inclined plane is the tool. What's the goal? To lift the box, right? The goal is to get the box from the ground up to here. So in order to do that without the ramp, so ignore the ramp now, we'd have to bend down, lift the weight of the box up to that height. So this height is going to be the D out. And this weight, the weight of the box, is going to be the F out. Because if we didn't have the tool, this is what we want done. This is the goal. Now we have the ramp, we have the tool. Using the ramp, we're going to push with some force. Because we're using the tool, that becomes the F in. And we have to actually push it a larger distance. That's going to be our D in. So we don't have to push as hard, but we have to push further. But I would much prefer this way than this way. I have one last main equation here, and that is the efficiency. Up there is the equation for efficiency, and over here I'll write the equation for percent efficiency, just so that you don't get confused. I mean, it's the same thing. I'm just going to translate it into percentage. There you go. So now that'll give you a percentage. You want to put a percent sign at the end of that. the percentage is how efficient the machine is, right? So how much energy you're putting in versus how much energy is it actually putting out. As I said before, no machine is 100% efficient. So we're always going to lose some efficiency. We're always going to lose some sort of energy. And that is usually lost between friction, heat, sound, light, and other types of transfers. Now, friction and heat are actually the same thing. Now, in your book, what's going to happen is that they may give you some forces and a distance and ask you to find the missing distance, but it won't tell you how efficient the machine is. In that case, you're going to assume 100% efficient. And that happens a lot in your book. They don't even tell you that. They're like, here's the AMA and the distance, what's the distance out? And you're like, and then you can just assume 100% efficient, even though we know that in the real world that it can never be 100% efficient. In your book, you can assume that for things that, if it's missing, you can assume 100%. You shouldn't be able to, no, because then that would be like adding energy. Like, where's that energy coming from? Like, we can lose energy because, and think about it, work in is the amount of energy you put into it, and then work out. Now, it can't create energy. It has to come from somewhere. It can lose energy. Again, it's not destroyed, it's just lost. So, because we can't create energy, then no. All right. The last little bit of information I have for you is compound machines. I think there's one question on a compound machine. To find the compound part of it, you just find the AMA of the first part and multiply by the AMA of the second part. So most machines are made up of lots of different little machines put together. You just multiply the AMA of all the little simple machines to get the full machine's AMA. And same thing with the IMA. And again, I think you only have like one question on compound machines. Okay, think about the bicycle. You have the pedal and the gear, and it's hooked to a chain, and then it's hooked to the back of the bike, the wheel itself. So you basically have two wheel and axle machines. So if you find the AMA of the gear and the AMA of the wheel, you should be able to multiply the two together.
Okay.
And the same thing goes for the IMA. Find the IMA of the gear and the IMA of the wheel and multiply them.
Okay, so when it says multiply the advantage of each simple machine, it's saying multiply AMA by AMA and then IMA by IMA.
Mm-hmm. Okay. And that'll give you your total AMA and IMA. And your machine could be more complicated than a bike. It could be like all the simple machines put together, or just like a whole bunch of gears put together. And you just multiply them all together. Okay, so let's do our practice. And I've got to stop this real quick.